So we've seen alkanes, so under the umbrella of hydrocarbons. Okay, we've seen saturated hydrocarbons. I'm going to abbreviate hydrocarbons as HCs. And these are our alkanes that have carbon-to-carbon single bonds. What we're going to see now is a much broader category called unsaturated hydrocarbons. And these are going to be characterized by having carbon-to-carbon multiple bonds. So we'll just introduce all of these now, and then we'll take a look at some examples. So we have what are called alkenes, and these contain carbon-to-carbon double bonds, so two lines between the carbons. We have alkynes that end in Y-N-E-S, and alkenes end in E-N-E-S. Alkynes have carbon-to-carbon triple bonds, so three lines between the carbons. And then we have what are known as aromatic compounds. And aromatic actually have, they're very distinctive because they have usually 6 carbons in a ring that look like this. And around that ring, we have alternating single bond, double bond, single bond, double bond, single bond, double bond around that ring itself. Sometimes that is abbreviated or it's shown as this structure. Something like this. It looks kind of funky, but what it is meant to show here is that there's a carbon at each of the point of this hexagon. That this is sometimes represented is sometimes you'll see a six-sided ring like that. So it looks like a hexagon, and there's a circle in the middle, right? That represents an actual structure. And if you see that in something, that tells you that it's aromatic. So what we're going to do now is take a look at some of these unsaturated ones, and we'll focus first of all on the alkenes and the alkynes. So our alkenes have at least one carbon-to-carbon double bond present in them. Okay, so for example, if I have a double bond between two carbons and I fill in the remaining bonds to H's, well, each of these C's will have to have 2 more lines. So I put those in. Then what I have is 2 C's, and then if I have fill in the H's, I have 4 H's. This is a molecule called ethene. Okay, and it ends in that E-N-E, tells you it's an alkene. If I have 3 carbons, so 1, 2, 3, and if I connect one of the, or 2 of them by a double bond, and then a single bond to the other, and I'm going to fill in now the remaining bonds to each of these carbons to H's, right? And this is actually a good practice to get the number of hydrogens in. So this first carbon here on the left side has 2 bonds to it. It needs 2 more. So 2 lines to H's. This one in the middle has 1, 2, 3 lines. So it needs a 4th one to an H. The one on the end here has 1 line to it. So it needs 3 more to the H's. So if I look at my formula then, the molecular formula, I have 1, 2, 3 C's, and 1, 2, 3, 4, 5, 6 hydrogens. This is a molecule called propene, and it has that E and E ending. All right, so again, the ending here kind of tells you what family it belongs to. So ethene, propene, and then let's do one more. So if I have 4 carbons, so 1, 2, 3, 4, and I connect them, if I connect 2 of them with a double, the remaining ones with single bonds, again, giving each of the C's enough bonds to H's to make sure that they have 4 lines around each of them. We could come up with the molecular formula. All right, so I have, let's see, 1, 2, 3, 4, 5, 6, 7, 8, and 4 C's and 8 H's. This is a molecule called butene. E-N-E again tells you that it's an alkene. All right, so alkenes are characterized by having that carbon-carbon double bond in their structure, And let's take a look at the alkynes. So alkynes, we can probably guess that these are going to be, the names for these are going to have that Y-N-E ending. So if I have a carbon and another carbon and they're connected by the triple bond, okay, each of these C's then is going to need one more bond. We're going to make that to an H. So I have two C's and I have two H's. This is a molecule called ethyne. So again, the Y-N-E tells you it's an alkyne. If I have three carbons and I connect two of them with a triple bond, okay, again, the first one here is going to need one more bond to an H. This one in the middle already has one, two, three, four. So it's actually good. Doesn't have any more bonds to make. The one on the end has three remaining. We're going to make those to H's. So we have one, two, three, four. So we have three carbons and four H's. This is a molecule called propine. The Y-N-E tells you that it is an alkyne. All right, so hopefully, what you're seeing so far is that there's a trend. Okay, the ending of the name kind of tells you what category or family of hydrocarbons they belong to. And the ending also tells you the type of carbon-carbon bonds that you have, right? Alkanes have carbon-carbon single bonds. Alkenes have at least one carbon-carbon double bond, and an alkyne is going to have at least one carbon-carbon triple bond. If we take a look at some of the aromatic compounds, okay, so something like the following. So this molecule that we drew before this, let me actually draw all the C's and H's so we can come up with the actual formula. So in an aromatic compound, we said we have an alternating single double, single double, single double bond, and we can now fill in the remaining bonds to each of these C's. So this carbon here at the top has one, two, three. Fourth bond is to an H. This C on the right here has one, two, three. It needs one more bond to an H. And as you go across or around the ring, you'll see that each of those carbons is in the same situation. They need a fourth bond to an H. So this has the formula C6H6. This itself is a molecule known as benzene. Okay, that's just a name for that. And whenever you see that in this structure, in any bigger structure, that tells you that it's aromatic. So aromatic compounds will contain this structure. And again, it's represented in a couple different ways. Sometimes you'll see the hexagon with the circle in the middle. All right, that just tells you that it's another way to represent aromatic. So that may be connected to a bunch of other carbons, right? As long as you see that that benzene in there, that tells you that it is aromatic. The double bonds in here, by the way, they're free to kind of rotate around. Okay, so so the alternating is what is the key thing here, alternating double and single bonds in the hexagon. We'll just call it a hexagon for now. Okay, so this is an example here of aromatic. So this is the characteristic of an aromatic compound is if you see this benzene ring in their structures. Right, so we've looked at several of these categories of hydrocarbons. Again, these just contain carbons and hydrogen. Hydrogen likes to form one bond, so it's kind of always on the outside. Carbon likes to be in the middle because it likes to be connected to itself, or to other carbons to either make chains or rings. So let's see how it can actually now form a ring structure, and we'll just use the alkanes as an example. So we'll take a look at ring or cyclic structures of some of these hydrocarbons. Okay, so in order to make a ring, you can't form a ring from one carbon. You can't form a ring of two carbons, right? So you need a minimum number of carbons, which is 3. So the minimum number of C's for a ring. So if I have a carbon and I have another one, Okay, in order to make that ring, I need to connect it to a third, and then I can close that ring like that. Okay, so I have three in a ring. I've connected them with single bonds. So right away we know this is going to be in some sort of an alkane. And I'm going to fill in the remaining bonds to carbon with H's. So this carbon here at the top of the ring has two bonds right now. It needs two more. That's going to be to H's. This one here on the left has two bonds. It needs two more. That's going to be to H's. The one on the right has two bonds. It needs two more. That's going to be to H's as well. So the formula for this is we have three C's, and we have a total of 1, 2, 3, 4, 5, 6. And we have three carbons. So if you remember all the way back up here, when we had three carbons in something, they all started with this name prop, right? So propene or propine, or in the case of the alkane, this one was called propane with three carbons. We're going to do that here as well. So we know that this is going to be a prop, three carbons. There are all carbon-carbon single bonds, so it's going to be an alkane, so propane. But this is not propane, right? Because if it were propane, we just set up here, propane should have the formula C3H8. This has the formula C3H6, so it's not propane. Instead, because now the carbons are in a ring, we call it a cycloalkane. Now, it's not a regular alkane, it's a cycloalkane. So we'd actually call this, not propane, we'd call it cyclopropane. All right. And if we extend that ring further, so if I had four carbons in a ring, so 1, 2, 3, 4, and I connected it, well, I have the same thing happening in each of these corners. I'd need two more bonds to H's for each of these to make the carbons happy. Well, I have four, so the way that we would call that is this BUT. And then it'll have the ANE because it's all carbon-carbon single bonds. And now it's in a ring, so we put this prefix cyclo in front. So this is cyclobutane, rather than just regular old butane that we saw. Did we do butane? I don't think we did butane. But butane would have four carbons in it. Cyclobutane has four carbons, but it's in a ring. Right? So this prefix cyclo here means that it's in a ring structure. Okay, and this is very common for carbon to form these ring structures. It does so very, very easily, especially when you get up to like 5 and 6 carbons. That those ring structures are actually way more stable than the open chain form. So this is another characteristic of your organic compounds, specifically the hydrocarbons that contain H's and C's.